All right, in this video we're looking at section 4.2, least squares regression. And our objectives for this are we are going to find the least square regression line and then use that line to make predictions. Then we're going to interpret the slope and the y-intercept of the least square regression line. And then we're going to look at this idea of residuals. So in the previous lesson, we talked about scatter diagrams and linear correlation coefficients. And once we know and we can see that two variables have a linear relationship, so first we need a linear relationship, we can find a linear equation that describes this relationship. Okay, one way to do this is to select 2 points from the data that appear to be a good fit. And once we find those 2 points, they appear to be a good fit for the overall trend of the data, we find the equation of the line using those 2 points. Okay, so here's, for an example, driving distance versus club head speed in golf. You can see that we've got this positive linear trend going on. And if we use the 2 data points, 99, so club head speed of 99 has a distance of 258, club head speed of 105 has a distance of 275. Okay, if we use those two, we can create a line, and that line is going to be a kind of a line of best fit using 2 points, and it's going to be an estimate for the relationship between the club head speed in miles per hour and distance in yards, all these points that we've gathered. So we're going to find the equation of this line that is on the graph and then use the 2 data points. So I should say the line that we're using, I mentioned before, when we only use 2 data points, is sometimes called the line of best fit. It's not the least square regression line. That's actually the best possible fit. But this is line of best fit is when you take 2 data points and we find an equation to model this experience. So we have the 2 points, 99, 258. Whoops. So that's our first point. And then we got 105 and 275 as our second point. And so we're going to find the equation of a line through these 2 points. So if you recall, a linear equation needs a point and a slope. So we got to find that slope. We have 2 points already, but we need the slope. So the slope is the the difference in the y value. So y2 minus y1 might sound familiar, divided by the difference in the corresponding x values, 105 minus 99. So when I subtract these, I'm going to get positive 17/6. So that's the slope of my equation. Then I'm going to use point slope form, which is y minus y1 equals m times x minus x1. It just requires a single point. And so I'll use this point right here, 105 and 275. You could use the other, you'll get the same equation. So I'd do y minus the y value equals the slope, 17/6 times x minus that x value. And then if I were to distribute in the 17/6 and add 275 to both sides, I would eventually get y equals 17/6x minus 45/2. Okay, that's when I go in and I do those calculations. I distribute, add the 275 to both sides. So this is our line of best fit right here. So now we want to find the predicted distance using the line of best fit for a club head speed that would be 103 miles an hour. So x represents that club head speed, so we would do y equals 17/6 times 103 minus 45 over 2. And when I multiply this out, I'm going to get approximately 269.3 yards. So now we have a prediction based off of 103. And actually that prediction is just, if I were to come up on here, that's right here, that would be the point, 103 and 269.3. And it's our best estimate using this line of best fit of what someone who swings a golf club at 103 miles an hour, what their distance will be. It does not necessarily mean that every person who swings at 103 will hit it that far, because obviously we've got this point up here that is above the line. However, it's a prediction that we can make now. Now, as I mentioned, there was a difference between this y value and the actual data point that we had. So our prediction was 269.3 for a distance when we were at a club speed of 103, but the actual observed was 274. So that distance right there is what we call the residual. Okay, and the difference between the observed and the predicted value is that residual. So when I take observed minus predicted, so we observed 274, that was the actual point, the actual data point, minus our prediction, that 4.7 is the residual. And so we go through and you can calculate all of these residuals with our line of best fit. Now our goal is to try and find the very, very best line where those residuals are minimized. We have the smallest possible sum of all the residuals. And this is what we call the least squares regression. Okay. And so again, the line of best fit just takes a couple of points that fit and we create a line. But when we want to get the best determination to describe the relationship between the two variables, that's based off of these residuals. The most popular technique for making residuals as small as possible is the method of least squares. Okay, and it was developed by Adrian Marie Legendry. I'm terrible at pronouncing names. But so here's the criteria for least square regression. You're not going to have to actually go through and know how all this works as far as the inner workings of the math to come up with the least squares, because that's calculus, and most of you probably haven't done that. But the least squares regression line is the line that minimizes the sum of the squared errors or residuals. Okay, now the line minimizes the sum of the squared residual, or the square vertical distance between the observed value y and the predicted value, which we will call y hat. So whenever you see y, that's the observed. Whenever you see y hat, that's a prediction. Okay, so we represent this as the minimized sum of residuals squared. And that's a lot of English there, but just know that when you see y hat, that's our prediction. So here's the equation for the least squares regression line. Okay, it's given by y hat equals b1, where b1 is the correlation coefficient times the standard deviation of the response variable divided by the standard deviation of the explanatory variable. And that's the slope. So we get y equals b1 times x plus b naught, and b naught is the mean of our response variable minus b1 times the mean of our explanatory variable. And that is our y-intercept. Okay. And then it talks about, reminding you what x bar, s sub x, standard deviation, those kinds of things mean down there. Okay. So now we're going to take a look at this data set. So we've got our data set here, and we want to first draw a scatter diagram and then comment on the type of relationship that appears to exist between X and Y. So I'm going to pull that up in StatCrunch, so give me just a sec, I'll be right back. Okay, so now we've got all of our data here in StatCrunch, and we're going to draw a scatter diagram. So here's our scatter plot. Again, our X variables are, our explanatory variable is already in X, and then Y will be our Y variable, our response variable, compute, and we can see here is our data in a scatter plot. It definitely looks like there is a downward trend. So we'd have some negative correlation going on here. If we needed to, we could come in, we could find out exactly what that correlation is. Okay, so it's pretty strong negative correlation. And then we could also find the mean and the standard deviations. So here are our means and our standard deviations to do our calculations. They do give those to us. And so now that we are given this information, we want to determine the least square regression line. And so again, here's our least square regression line. So first we need to find B1. Okay, and again, B1 is R times S sub Y over S sub X. Okay, and this is going to be negative 0.9477 times 1.8239 divided by 2.4221. Okay, and that is approximately negative 0.7136. So that is B1. And then B sub naught is going to be equal to, so we got, so Y bar minus B1 times X bar. So we'll have 3.9333 plus, or excuse me, we were minus on this one. It'd be minus negative 0.7136, and then that was multiplied by X bar, which X bar for us is 3.6667. Okay, and then that is approximately 6.550. So our least squares regression line is going to be Y bar equals negative 0.7136 X plus 6.550. And that would be the least squares regression line. Okay, those calculations are a bit tedious, but know that StatCrunch is going to be able to help us out greatly, and there are many calculators that can find the least square regression line once you have the data set. So that will end us for part 1, as we're looking at our line of best fit, least square regression. We'll get more into the StatCrunch and the nitty-gritty in the next video, but I appreciate your time.